Hi, my name is Thomas Wayne, and for my Capstone project, I will be building and launching a model rocket. Now, my capstone started with a very simple idea. I just wanted to make something by myself using all the things that I learned in high school, because as beautiful as those equations are, they don't really do anything sitting on a page. And so from this idea, I began exploring my options until I decided on model rocketry, because A, I loved rockets and airplanes since I was a kid, B, it connects to my future field of study, which is aerospace engineering. So I hope this project was able to teach me a few things about the engineering side of airplanes and rockets. I started by researching the basics, types of model rockets, safety rules, engine types, how to recover a rocket after launch. And it was surprising to see how many different types of rockets there were on the market, depending on how high you wanted a rocket to fly, how many parts it had, and what type of payload you wanted it to carry. I ended up choosing the ST's Tandem X model set because it was a very beginner-friendly model kit, and it also had two rockets for me to launch, the Crossfire and the Amazon, which is the one you are seeing me build in the background. One challenge I ran into early on was finding the right tools. Although most of the materials were already included with the package, there were tools like hobby knives, plastic glue, and sandpaper that all had to be bought individually. Another major challenge was finding a good location to launch. I had no idea how strict the rules were, but I knew that I needed space, permission, and safety clearance to launch my rocket. After going through a lot of documents, what I basically found was that you couldn't launch it anywhere within these red circles. The place I ended up choosing as my launch site was Mud Bay Park, because firstly, it was a public park, which meant I didn't need permission to access it. Second, it was probably the safest launch site that I could choose, because it was not within the range of any of those circles, and it had a 500-acre mudflat for me to launch my rocket on. Now that my preparations are complete, it's time to finally build the rocket. Going into this project, the most experience I've had with building plastic models was from LEGO, so I was absolutely terrified and nervous when I first started working with this. So many things could go wrong, like if I broke a small piece, the whole rocket would be compromised and I would need to buy an entire set just to replace those tiny pieces. Luckily for me, I managed to not break anything important, yay, and things actually became a lot quicker when I finally figured out where everything goes. However, gluing everything together turned out to be quite tricky. The glue that I used set very slowly, but once they did that, they basically were impossible to get off. So overall, this made my workbench extremely messy. As I was finishing up my rocket, I went on to go check the weather to find a favorable time to launch my rocket where it would be sunny and there would be no wind. But that's when I realized something. So you know how earlier I said that the park was a safe place to launch my rocket? Well, almost. Because while the open field provided me with a great space to launch my rocket, there happened to be a highway located just around half a kilometer away from my launch site, which means that I risk a possibility of my rocket going onto the highway as it was descending. And so, to remedy this problem, I will have to calculate how far away I need to launch my rocket away from the highway so that the wind wouldn't push the rocket towards the highway as it was descending. Alright, so to start our calculations, let's take a look at the forces at play here. So we have the drag force, which is equal to 1 over 2 PV squared AC, and we have the gravitational force, which is equal to mg. Now P means the air density, V is the vertical velocity of the rocket as it is falling down, A is the area of the parachute, and C is the coefficient of drag. We are trying to find how long it would take the rocket to fall down, because this time multiplied by the wind speed will be the horizontal distance in which the rocket will travel as it is blown by the wind as it is falling down. And this horizontal distance is important because this will help us determine where we are going to launch our rocket, so that as the wind is pushing this rocket, when it's falling down, it will not hit the highway over here. Alright, so now let's get to the actual calculations. So the net force is the gravitational force minus the drag force, which could be also turned into this equation over here. So MA is the m dv over dt, which is equals to mg minus 1 over 2 dv squared acd. Now we will put alpha, we'll substitute alpha as the square root of the drag force. And we will explain this later, but this will just help us with our simple calculations. And after we substitute everything in, this is what we get. Alright, so now that we moved everything to the right side, we can begin to integrate. Now, this function by itself looks really hard to integrate. Got a lot of variables, and this just doesn't really seem right. But what we can do is find a similar function, which is the derivative of arctan h. And then we see that these two functions are very similar, and we could just say that x goes to alpha v. And so now by integrating these two functions, and the integral and the derivative cancels out, we can say that t equals to arctan h alpha v divided by alpha g. And since we want the graph as v in the function of t, we're going to move everything until v equals tan h alpha gt divided by alpha. And remember earlier how I said alpha was the square root of the drag force? Alright, now we're just going to plug everything in. So using data from our lab, we see that P, which is the air density, goes to 1.225. Area of the parachute is 0.0585 meters squared. The coefficient of drag, according to NASA, of a standard model rocket parachute is 1.5. The mass of my rocket was 0.2 kilograms, and the gravitational constant was 9.8. So alpha ends up being 0.116. And when we plug everything together, we get this graph. Now, this graph by itself won't tell us what the time is. To find the time, we must know the area under the graph, which is similar to the displacement or the max height. Now, conveniently, the rocket path just tells us how high the rocket will approximately fly, which should be 200 meters. So, to find the area under the curve, we simply must integrate the function again, and which we set the area as 200 meters. We can then simply find t. Now, when we plug everything in, t is shown by this blue line over here. And this blue line lands on around 33.62 seconds. Bam. That is our most important value in this entire equation. So now that we know how long it would take for the rocket to fall down, we can simply multiply that by the wind speed, and we will get a horizontal displacement. So on that day, the wind was blowing 17 miles per hour. find a horizontal displacement, which is the wind speed multiplied by the time, which gives us around 255.5 meters northeast. Now, it is important to note here that we are neglecting the horizontal displacement caused by the wind as the rocket is going up, because it's going up so fast, the is really small. And also, we are neglecting any lift caused by the wind as the rocket is going downward, which could possibly increase the time. Alright, now that we have our displacement, we can choose our launch point. So the launch point I chose was this location. And it is directly 330 meters south of the highway. Which means that as the rocket is traveling northeast, it will not land on the highway. And even if the wind direction changes, directly blowing north, it will still have an 80-meter gap for the rocket to land. Alright, now that we're done with all the math, it's time to put our rocket to the actual test. On launch day, everything went relatively well, except for the fact that the engine cap on my Amazon rocket broke off, making it useless and unable to be launched. Fortunately, I still had the Crossfire rocket left, so that was a rocket that I had to launch, and it had to work, or else this whole project would have been for nothing. And now, as I am approaching the beach, I see my reference point, which tells me approximately how far away I need to go. So before I show the footage of the launch, I would just like to apologize for my off-road camera skills, because I was holding the controller with one hand while recording on the other. Things got really shaky. This project taught me more than I expected, not just about rocketry, but about patience, problem solving, and creativity. I got a real sense of what it means to work on a long-term project. Things didn't always go perfectly, but I learned to adjust, research better, and keep going. It's one thing to study Newton's law in class, but it's another thing to see them in action, in something you build yourself. I also learned that engineering and design are as much about asking good questions as they are about finding answers. Why did the rocket tilt a little? What could improve the parachute deployment? These questions made me think more critically and deeply than any worksheet ever could. Personally, this project reminded me of how much I love creating things. It was fun, but more than that, it was fulfilling. I feel more confident now in trying hands-on projects, even if they seem intimidating at first. I'd love to explore multi-stage rockets, or even adding a small camera to capture the flight. I might take some time this summer to work on a new version, maybe even design my own forms from scratch instead of using a kit. I'm not sure yet, but I know this won't be my last launch. Thank you for watching my capstone journey. I hope this inspired you to explore something that excites you, even if it's outside your comfort zone. For me, launching this rocket wasn't just about flight. It was about curiosity, creativity, and doing something I'll never forget. Thank you.